Let's look at another example. So this time we've been given a component, so a bar, which has an outer diameter of 50 millimeters, but it's got a blind hole or a blind ball in it. And that blind hole has a depth of 0.2 meters and it's got a diameter of 30 millimeters. That component is being subjected to a tensile load of 10 kilonewtons, and we've been tasked to do the following. We're being told to calculate the stresses in the section of the bar. Okay. We've also been told to predict the total extension due to the applied force, and we've been told to assume the Young's modulus, or the modulus of elasticity, A, to be equal to 200 GPa. And we've also been given a third challenge. So assuming that the component is subjected to a uniform temperature change of 20 degrees C, what is the measure of the thermal stress? And we've been told that for the material, the coefficient of linear expansion, alpha, is equal to 12.5 times 10 to the power minus 6 per Kelvin, what we just worked out. So similar to the previous problem, it's smarter to segment the component into two separate parts. So the hollow section, we're going to cut across that surface over there, and that will constitute one section of the component, and the solid section will constitute another segment of the component.
Let's work through this problem. So this time we've been given a bar which has a blind hole drilled into it. And we're tasked to calculate how much this component extends if it's been subjected to a tensile load of 10 kilonewtons. So how do we go about working through such a problem? Well, it's no different from working out or calculating that of a stacked bar. It's more or less the same principle. So what we can do is we can segment the components into two distinct sections. So the part or the region that doesn't have the hollow going through it, we can call that section 1. And the part that has the hollow through it, let's call that section 2. So similar to the previous examples that we've looked at, we can calculate the stress of the solid section separately, do likewise for the hollow section, use the equation for compatibility with respect to having equal forces in both sections to work out the stress for the other. And we can use the same concept in calculating the strain in one section to calculate the extension. Do likewise for the other section, add the two to get the total extension experienced by component. Right. So let's do that. So for section 1, the area A1 will be equal to pi over 4 d1 squared. Now I do need to point out not all problems will have the cross-sectional profile being circular. Okay, it kind of like seems that's the case with most problems, but when it comes to engineering components, I think we tend to look at circular components a lot. But again, devoid of what the sectional profile is, as long as the sectional profile is calculated correctly, then it shouldn't really matter. So I'm just pointing that out there if it seems that calculating circular profile seems a bit repetitive. Just the nature of the question. Okay, so the diameter is given as 50, so pi over 4 times 50 squared. So pi 4 times 50. So that gives 1963.5 millimeters squared. So we can calculate the stress. So the stress in section 1. So let's call that sigma 1. That'll be equal to F divided by A1. Okay, so that'll be equal to 10,000 newtons divided by 1963.5. So we do the computation, so 10,000 divided by 1963.5, that gives 5.09, let's call that 0.93 Newton per millimeter squared. So that's the same as 5.093 MPa. So we've worked out the stress and the area in section 1. So when it comes to section 2, the area A2 will be equal to, so again, don't forget that this is a hollowed section. So if we reflect on what we did in the previous question, I stated that A2 will be the difference of the area of the solid section minus the area of the hollow section. Okay? And since that is circular, we are going to be using pi over 4d squared. Okay? So since pi over 4 will be common to both terms, then what we can do is we can rewrite that to be pi over 4 times the difference between the diameter of the solid section squared minus the diameter of the hollow section squared. Okay, so this becomes pi over 4 into brackets the hollow section given as 50, the solid section given as 50 squared, and the hollow is given the problem to be 30, so that'll be 30 squared. So this becomes 50 squared minus 30 squared. So pi over 4 times 1600. Pi. And that gives the area to be 1256.64 millimeters squared. Alright. So since the tensile load F is equal to the tensile reaction in section 1, which is also equal to the tensile reaction in section 2, then this implies that the product of sigma 1 times A1 is equal to sigma 2 times A2. So since we're trying to solve for sigma 2, if we make sigma 2 the subject, then the stress in section 2, sigma 2 will be equal to sigma 1 times the ratio of area 1 to area 2. So this becomes 5.093 times A1. So A1 was 1963.5 divided by 1256.64. So if we bring our trusted calculator, so this becomes 1963.5 divided by 1256.56. Multiply that by 5.093, and that gives 7.96. Okay, let's do that 95 So I left that in 3 decimal places. I'm going to leave this in 3. So that'll be 8 MPa.
This is required.
So we've done that part.
So,
So the next part,
similar to what we did in the work along, the solid section, section 1, we've been given some information in terms of how long it is. So that section spans 0.1 meters and the diameter spans 50 millimeters. So we proceed to calculate the cross section of the given component or the given section. So A1 for section 1 is equal to pi over 4 times the diameter squared, and if you do the computation we get 1963.5 millimeters squared. We do likewise for section 2. So for the hollow section, the area is equal to pi over 4 times the difference of the outside diameter squared minus the inside diameter squared. So this will be equal to pi over 4 times, into bracket, 50 squared minus 30 squared. And that gives an area of 1256.64 millimeters. So what we can do is we can calculate the stress for one area. Or if we want to, we can just calculate the area separately. Either way will give you the same result. So you can use the concept of compatibility to work out the stress for either one of the sections. So since stress is equal to F over A, so F is the applied force and A is equal to the cross-sectional area, then for section 1, sigma 1 will be equal to the applied tensile load divided by its cross-sectional area. So that'll be 10,000 divided by 1963.5, and that gives 5.093 MPa. Okay, and we can round that down to 5.1 or 5.09. We do likewise for section 2, and that will be sigma 2 will be equal to 10,000 divided by 1256.64, and that gives a result of 7.958 MPa or 7.96 MPa or 7 or 8 if you want to do it that way. But it's always best to leave a few decimals since we're still doing some computation on the given problem.
so we've done that part. So the next part is to calculate the extension. So what I'm going to do is I'm going to take a bit of a shortcut because I think in our previous discussion, the total extension, so that is delta LT is equal to the extension in section 1 plus the extension in section 2. So let's call this equation 3. Alright, but we previously deduced that to calculate the extension with respect to the stress and the Young's modulus, delta L or delta I is equal to sigma I over EI multiplied by the original length. So we deduce this equation from the previous problem. So this at least saves us a lot of time. Right? But if you're unsure, then what I suggest you do is calculate the stress with respect to the stress, calculate the strain with respect to the stress and the Young's modulus. And from there you proceed to use delta L is equal to epsilon times the original length. Okay, this is just saving time. Alright, so extension in the solid section, or section 1 as we've called it. Delta L1 is equal to sigma 1 over E1. The component's homogeneous, so we don't really need to have different values of E for the sections of the component. Unless the composite, then that's a different story, depending on the nature of the composite. Times the length of that particular section. So this will be, so we calculate the stress to be 5.093 divided by E. So E in this particular problem is given as 200 times 10 to the power of 3. So similar to the previous problem, I'm working these out on the basis of millimeters just to save time. But if you are unsure, then what I suggest you do is you calculate your variables in the basis of meters. So this would be 5.093 times 10 to the power of 6 divided by 200 times 10 to the power of 9 times the length, which would be in the basis of meters. So this would be 0.1. Alright? So let's not forget that. But the original length is 0.1, which is the same as 100 millimeters. Right? So times 100 millimeters. It all comes down to the question. So if the problem tells you to express your final result in meters, then you need to ensure that you express it in meters. So 5.0393 divided by 200 to the power of 3 and 100, and that would give 2.5465 times 10 to the power minus 3 millimeters. So that is for section 1. For section 2, the extension delta L2 is equal to sigma over E subscript 2 times the original length. The original length in the problem, I think, was given as 0.2 meters. So this is the same as 200 millimeters. Right. So this becomes 7.958 divided by 200 times 10 to the power of 3 multiplied by 200 millimeters. So this becomes 7.958 divided by 200 to the power of 3. Okay, and multiply that by 200. And this gives 7.958 times 10 to the power minus 3 millimeters. So therefore, the total extension experienced by the widget delta LT is equal to 2.5465 plus 7.958 to bracket. So I've intentionally factorized the minus 10 to the power minus 3 out, just to make life a bit simpler. And this gives 2.5465 plus 7.958. This gives 10.5045 times 10 to the power minus 3 millimeters. Okay. Or what we're going to do is just divide that by 1,000. Again, this is also 0.011 millimeters, approximately.
Computation on the given problem. Okay. Now that we've calculated the stresses in each section, we can then proceed to calculate the strain. So the strain is equal to the ratio of the stress to the Young's modulus. So epsilon 1 is equal to sigma 1 divided by E, or you can write it the way that I've written it here, which would be sigma 1 times the inverse of E. So they more or less mean the same thing. So sigma 1 was calculated to be 5.039 times 10 to the power of 6. So that's the M. So don't forget that M is mega. Times the inverse of 200 times 10 to the power of 9, and that gives a result of 2.5465 times 10 to the power minus 5 as the calculator's strain. And don't forget, strain is dimensionless. Okay, we do likewise for section 2. So the strain in section 2 is equal to the stress times the inverse of the Young's modulus. So if we've had a situation whereby the material is constituted of two different materials, then we use its provided or known Young's modulus. So this is equal to 7.958 as previously calculated times 10 to the power 6 divided by or multiplied by the inverse of the Young's modulus, which was given as 200 times 10 to the power 9, and that gives a calculated strain of 3.979 times 10 to the power minus 6. So to calculate the extension, so delta L, that'll be equal to the original length for that section of the bar times its predicted or calculated strain. So 0.1 times 2.5465 times 10 to the power minus 5 will yield 2.5465 times 10 to the power minus 3 millimeters. Or you can express this as 2.5465 micrometers if you wanted to. Right? And we do likewise for section 2. So the extension in section 2 will be equal to the span of that particular section, L2, times the predicted or calculated strain, epsilon 2. So the product will give a result of 7.958 micrometers, or times 10 to the power minus 3 millimeters. So the total extension experienced by the component will be equal to the sum of the extension in section 1 and section 2. So if you add the two extensions, this leaves a result of 10.5045 times 10 to the power minus 3 millimeters.
So the last question to this particular problem, I'm being told that assuming that the components, so we have our components, so we've got our components, and for some reason that's been heated. To cause a temperature change. So the temperature change, or if you want to call it temperature differential. So temperature change, so in some books they'll say delta theta to represent that. I tend to use delta T. Okay, so it's up to you. And that's given as 20 degrees centigrade. Alright. We're being told to calculate the measure of the thermal stress. So in addition to the temperature change due to the applied tensor load in section 1 and section 2 of the component, I'll also remember that we talked about thermal stresses under chapter 4, and any incremental or temperatures, so reduction in temperatures can cause additional stress within the component. So let's calculate what this additional stress is based on the temperature change. The coefficient of expansion, so in this case linear expansion, alpha, in the problem was given at 12.5 times 10 to the power minus 6 per Kelvin. Okay. Now, when it comes to this problem, it doesn't really matter, because when it comes to the conversion from Kelvin to degree C, you just need to add 273.17, I believe, to whatever the temperature is in degree C. So the difference would more or less take the Kelvin component out, so we don't really need to worry too much about that. So either way, it doesn't really matter what the difference would be. So the difference can be in Kelvin, so the difference could be 200 to 20K, since we're dealing with temperature difference as opposed to initial temperatures in degrees Kelvin and the final temperature in degrees Kelvin, in Kelvin, sorry, it's not degrees Kelvin, in Kelvin. So we don't need to worry too much about that. So we don't need to do any conversion in terms of the coefficient given. Right. So to calculate the thermal stress, so let's call that sigma T. That'll be equal to the product of alpha, the temperature change, and the Young's modulus. So this makes life easy. So again, it might be worth that if you're not familiar with this equation, you visit chapter 4 on our discussion relating to thermal stresses and how those equations came into being. So it might be worth revisiting that particular topic again before coming back to the work along. So this would be equal to 12.5 times 10 to the power minus 6 times 20 times E, 200 times 10 to the power of 9. So let's bring our handy calculators to 12.5 times 10 to the power minus 6 times 20 times 200 times 10 to the power of 9. And that gives 1, 1, so that is about 50 times 10 to the power of 6 Newton per meter squared. Okay, so that is our mega, so this is the same as 50 meganewton per meter squared, which is the same as 50 MPa. So the temperature change in the component will induce a greater stress compared to the applied tensile force of 10 kilonewtons.
We're also given the problem to calculate the thermal stress if the temperature change, the component experiences a temperature change of 20 degrees C. So from a previous lesson that we did, so I think this is relating to chapter 4, when we briefly talked about thermal stresses. We can calculate the thermal stress by multiplying the coefficient of linear expansion or thermal expansion by the temperature change or the temperature differential by the Young's modulus. So this becomes 20 times 12.5 times 10 to the power minus 6 times 200 times 10 to the power of 9, and this gives us a result of 50 times 10 to the power of 6 Newton per meter squared, which is the same as 50 megapascal. And there we have it. Alright folks, so hopefully everything made sense to you. So any comments that you have, can you just type it down below? And hopefully you join me in the next session. So please share and subscribe, and I'll catch you in the next section. Bye for now.